Got it. Here we go. So did you guys revise previous classes? Good afternoon, people. So finally, we are done with building the prerequisite of set theory. And once we are done with building the prerequisite of set theory, then now we can go ahead and we can. Good afternoon. Okay. Now we can go ahead and start understanding probability. Some people pronounce it probability. Some people pronounce it as probability. Whatever. So just to give you a very quick recapitulation, the observations so far. Number one, what is a random experiment? मेरे सवाल आपके जवाब. Somebody please come forward and tell me what is a random experiment.
We cannot predict the outcome, sir.
We cannot predict the outcome. What is a sample space?
Possible outcomes in a set. All
possible outcomes or all possible outcomes?
All possible outcomes of a random experiment.
All possible outcomes of a random experiment. Event.
Subset of sample space, sir. Even it is a part of sample space.
It is a part of sample space in
that
which
we are interested. In which we are interested.
Wow. And then we performed certain operations on set. What is complement of a set?
A set that does not belongs to A.
Complement of A is everything that does not belong to A. Perfect. And what is intersection of two sets?
Common part of A and B.
Common points of A and B. Intersection of A and B are the collection of common elements of A and B. And what is the difference of A and B? What is the difference
A minus
of A and
A intersection B?
The elements which are eliminated.
Sir,
elements
A minus
of
A
B.
intersection B.
Elements of B that are eliminated from A.
Elements of B removed from A. Only those elements which are present in A. So A minus A intersection B. So A minus B and B minus A. Both will be the same things, no?
No, sir.
No, sir.
A minus B and B minus A, they will not be the same things. Okay. And then we also learned about union. What is union of A and B?
Elements belong to A or B or both.
A or B or both. Wow, lovely. So elements belonging to A or belonging to B or belonging to both. Then we understood certain laws. And the very first law is we understood certain laws of sets. And the very first law is the law
Associative.
De Morgan's.
Sir, associative law and distributive law.
Associative and distributive. What is associative? A union B, and then you perform union with C, or you perform B union C and then you perform union with A. Means sequence does not matter. Same thing with intersection. A intersection B, and then you perform intersection with C, or you perform B intersection C, and then you perform intersection with A. What is distributive law? This was associative law of union and associative. Hi, sir. Is there any dedicated practice course available? Yes. 12th of April. And we are starting a dedicated practice and test and revision rank booster batch. But if somebody, I will reveal the details in 1 or 2 days. Don't worry. 12th of April after bark, it is starting. Okay. So you can go to www.unmatchable.in and check. So what is distributive law? Distributive law of union and intersection. Somebody come for it.
A union B,
A union C.
union
A
B,
union.
B intersection C.
Intersection A union C. Sir.
Okay. A union of A and B intersection C. This will be equal to what?
A union B intersection A union C, sir.
A union B intersection A
A
union
union C.
A union C. There is one more. There is one more. What
A
is that?
intersection of B union C, sir.
A
Intersection B
and
union.
B union C, and I'm going to take intersection of both of them. So what will be its result? It will
A
be equal to what?
intersection B. A intersection B union A intersection C, sir.
A intersection B union A intersection C. And then we entered into De Morgan's laws. What are De Morgan's laws?
A union B complement equal to
Say it.
A union B complement equal to A complement intersection B complement, sir.
A union B whole complement is A complement intersection B complement. Second law of De Morgan.
A intersection B whole complement equal to
A intersection B whole complement is equal to
A complement union B complement, sir.
A complement union B complement. Last law.
Inclusive.
What do you call
exclusive
it?
principle, sir.
What is the name of that principle?
Inclusion,
Exclusion,
exclusion
and
principle, sir.
exclusive.
Inclusion exclusion principle. And how do you write it?
A
Number of
union B
elements
equal-
present in A union B is equal to number of elements present in A plus number of elements present in B and
minus
minus or plus
minus, sir.
minus number of elements present in A
A
intersection B.
intersection B.
So do you remember inclusion exclusion principle for 3 sets?
Yes, sir.
A union B union C, number of elements will be equal to number of
A
elements
plus
in
B
A
plus-
A
plus number of elements in B plus number of elements in C minus
minus
A intersection
union-
B, sir.
A intersection B minus B
Minus
intersection
B
C
intersection C minus C
minus
intersection
C
A
intersection C. A.
plus A intersection B
minus A
intersection C, sir.
intersection B and B intersection C and C intersection A. That's it.
Plus A intersection B intersection C, sir.
Acha, A intersection B intersection C we add finally. Perfect. So far, so good. Random experiment is anything whose outcome is not fixed. Anything that you observe, for example, rain will happen today, outcome is not fixed. So that's a random experiment. What will be the temperature tomorrow at 1 p.m.? Random experiment. How much time a person will take in an ATM booth? Random experiment. How much time will it take for you to cross a railway crossing? Random experiment. After what age a person will die? Random experiment. How many fruits a tree is going to bear? Random experiment. Okay, so then you look around and you will find we are surrounded by randomness. There is so much randomness around us. We don't know with definiteness that what is happening. So something whose outcome is not fixed, that becomes random experiment. And sample space is nothing but collection of all possible outcomes. Sample space is simply a set of all possible outcomes. That outcome is not fixed, but I can at least I can list all possible outcomes. That becomes sample space. Event is only one part of the sample space in which we are interested. At a particular crossing in a city, an accident will happen or not, that's a random experiment. But suppose we are interested in two accidents happening on a particular day, that's an event. We are interested in knowing that what is the chance that exactly two accidents will happen. That becomes an event. What is the chance that at least three accidents will happen? That becomes an event. What is the chance that no accident will happen? That becomes an event. An accident will happen. That's a random experiment. May happen, may not happen. One accident might happen. Two accidents might happen. Three accidents might happen. Four accidents might happen. Okay? You call one of your old friends is a random experiment. Why? Because he might answer your call, he might not answer your call. But what is the chance that your friend will talk to you for 5 minutes over that call? Now that is an event. That's a specific thing you are interested in. There are so many outcomes possible. He might answer your call, he might not answer your call. If he answers your call, he might say, hey, look, I'm very busy, I'll call you back. Or he might start telling you that, look, I went on this trip and then there we did this, we did that. And you're like, I called for my purpose and this guy is, boring me for last 10 minutes. And then finally you gather the courage and you say, man, listen, I just needed your credit card or something. Then he's like, okay, that's what you called for, huh? So event is you are interested in something. The part of the sample space in which we are interested, that becomes event. The part of sample space in which we are interested, that becomes an event. That becomes an event. Complement everything except A. Everything except A. So complement is everything except A. Intersection is what? Intersection is that only that element I'm going to entertain, only that element I'm going to consider which belongs to A, and also it belongs to B. So and is a very, very, very important condition here. Union of A and B, I'm going to consider all those elements which either belong to A or belong to B or belong to both. That is union. Then all other laws we have already understood. These two are called by the name De Morgan's laws, and these two are called by the name De Morgan's laws, and this one is known as inclusion-exclusion principle. This one at the last is known as inclusion-exclusion principle. Perfect. If you are okay with all these things, we can go ahead and start understanding and start attacking probability. You understand these things, then we can start attacking probability.
Sir,
Okay, sir.
Union A union B in the point of probability means occurrence of A or B or both, sir.
Yes. From the point of view of probability, intersection means occurrence, simultaneous occurrence of A and also B. But when you say union, then it is the occurrence of A, or it is the occurrence of B, or it is the occurrence of both. Means at least one happens. Either A happens or B happens, or maybe both are happening.
Okay,
Cool.
sir.
Now, there is one very good way to represent all these operations. What is that? To represent all these operations, whether it is complement that you are
Venn
representing,
diagram.
Venn diagram, and whether it is intersection that you are representing, or it is difference of B from A that you are representing, or it is union of A and B that you are representing, whether it is difference of A and B that you are representing, or it is union of A and B that you are representing, there is one very interesting way. And that interesting way is here, complement of A will be represented by everything other than A. Venn diagram is actually a very powerful tool. Some problems that you otherwise solve in a very complicated manner, they can be solved using Venn diagram just like that. Now, intersection is only this common part of A and B. What is the difference of A and B? Remove everything from A that belongs to B. From A, you remove everything that belongs to B. And what is A union B? A union B is encompassing everything, either A or B or both. You cover everything. Cover everything. That's how union is defined. So now we are ready to go ahead to the third topic and start understanding probability in case of finite sample spaces having equally likely elements. In case of finite sample spaces having equally likely elements. Here we go with finally with the third chapter, that with the third topic, and the third topic is understanding probability itself. Now, what is probability? Probability is chance of occurrence of something. Probability is chance of occurrence of something. Probability is chance of occurrence of something. That what is the chance? What is the chance of raining today? What is the chance of raining today? So we give it a mathematical representation like this. What is the probability of raining today? What is the probability of raining today? This kind of mathematical representation is given. What is the chance of, what is the chance of an aspirant? What is the chance of an aspirant getting a, what is the chance of an aspirant getting a double digit rank in GATE? What is the chance of an aspirant getting a double digit rank in GATE? My dear friends, we give it a mathematical representation like this. Probability of a double digit rank. Probability of a double digit rank. This probability is 0.37 if you are a student of Mission DDR batches, and 0.04 if you are a student of other batches. I'm not saying that even in DDR batches you are going to get this, but probability is, of course, very much high. Why? Because of the grilling that takes place for whole year, because of the discipline that is forced on you for whole year. Now, similarly, you can keep asking, what is the chance of an accident at a crossing? What is the chance of What is the chance of timely arrival of a train? What is the chance of timely arrival of a train? So now you give it a mathematical symbol that what is the probability of train arriving at time? What is the probability of train arriving at time? What is the probability of, what is the chance of King Kohli scoring more than 50 runs today? So you give it a mathematical representation like this, that runs that Kohli score are more than 50. What is the P of that? So you write P and then bracket. The big question is, how do you get these values? The big question is that how do you get these values? The big question is that how do you get these values? How do you get these values? How exactly do you get these values? This is going to be our main mission today, in today's class, in current session, that we should be able to think like a scientist, or think like a curious person in the mid of 19th century, when probability theory was still not there. I know that you are going to answer, sir, hello, sir, I know, sir, favorable elements upon total elements, that is probability. Sir, favorable elements upon total elements, that is probability. No, that is not probability. Probability, the probability in a form that has been taught to you, that probability is, I know that it has been taught to you like this, that probability is favorable elements upon total elements. This is total BS. This is total BS. This is not probability. Believe me, and I will prove this in today's session, that this definition of probability that you have studied, favorable elements upon total elements, this definition is not actually a fundamental definition of probability. This definition is not going to work in so many cases, believe me, because you don't have total defined. You don't have total defined. What is the probability that one customer will appear right now at my restaurant? Sir, you have a restaurant? No, it's a hypothetical question. What is the probability that one person will appear, one person will put an order from my restaurant right now? You tell me, what is the total here? Total here is whole city. And maybe a person who arrives from Mumbai to Lucknow just today, he also is included. And maybe a person who arrived from New York to Lucknow today might order from my restaurant. Maybe a person who just landed from Sri Lanka to Lucknow, maybe he will order from my restaurant. So I don't know the total. And therefore, when this definition of probability, favorable elements upon total elements, is spoon-feeded to you, you need to question that, sir, what is the probability that right now a person will enter into this ATM booth? What is the total? Where is the total? Huh? What exactly is total here? What exactly is total? I mean, people are running beside that ATM. So this person can also enter into that ATM. This person can also enter into that ATM. This person can also enter into that ATM. A person who arrived from, let's say, Bangalore to Lucknow today, he might be going from airport to his native place. And on the way, he will say to the cab wala that, sir, listen, stop by. I need to withdraw some cash. So you don't know the total. And therefore, what is probability? That we understand how we get that probability value. That is our mission. That is our big question mark. How we calculate that. My dear friends, before you can build a theory of probability, you will have to start with some axioms. Axioms are belief. Axioms are our core belief. Can we prove them? No. Can we ever prove them? No. Axioms are just something that we believe in. For example, we believe in few things. For example, God is there. Can we prove God is there? No. That's an axiom. God is there. We believe that uh, working out every single day is going to prevent so many diseases. Is it like something that we can prove? If a person is working out, is it a guarantee that he will not get a disease? No, we believe that. We believe, of course, these beliefs are generally based on some observations only. These, I mean, belief should not be kind of some weird thing that no, I believe that sun rises from west. Your belief is absurd then, but your belief is called axiom. And before we build the theory of probability, we are going to propose such three belief. Belief number one, that any event in the world, can never have a negative probability. Any event in the world can never have a negative probability. Worst case, it can have zero probability. You verify this axiom with your observations. Axiom number one. So try understanding solving probability or answering this mysterious question that what is the chance of an aspirant getting a double-digit rank in GATE? What is the chance of raining today? What is the chance of timely arrival of a train? What is the chance of Kohli scoring more than 50 runs in today's match? How do we get the answer of these questions? Initially, these questions were the questions of interest only for gamblers. But as science progressed further and further, people realized even science doesn't have the capacity of modeling each and everything deterministically. I toss a coin. I know that even science cannot tell me, with no matter how many laws of motion you apply, and with no matter how many quantum theories you apply, if I toss a coin, even science cannot tell me that exactly the coin is going to land with a head on the top or with a tail. So coin is a tail will appear or a head will appear. So even science later accepted that if we are living in this real practical world, we have to accept that randomness is there. We cannot predict each and everything absolutely. And therefore, we should be able to get an answer of these questions that, okay, I don't know if it will happen absolutely 100%, but can I know what is the chance? Because on chance, if chances are more than 90%, then I will go out. Because I know that accident will not happen, 90% chances are there. If train arriving at time is having 90% chances, then I will go on the station at time. Because I know then if train arrives at time, I might miss the train if I don't go to the station. If chance of Kohli scoring more than 50 today is very high, then maybe I'm not going to post any trolling comment against King Kohli on social media. Otherwise, I will be trolled. So guys, I want to know these chances. How do I answer these chances? To answer these chances, people started with some belief, some core belief. To answer these questions people proposed 3 axioms. Axiom means what? Axiom means a belief. Axiom means that we believe this to be true. Can it be proved? No. They proposed 3 fundamental axioms of probability, and that's going to be our first subtopic under this interesting topic of probability. So my dear friends, here we go with the 3 axioms. What are axioms? Axioms are our belief. For example, one such belief is energy of the universe is conserved. Who measured? Did you measure the energy of whole universe ever? Did you measure the energy of whole universe ever? The mass of whole universe is conserved. Ooh, huh? I don't believe your argument. Can you prove it? That the mass of whole universe is conserved? The other person is going to say कि भाई हमें माफ करो कौन से पागल से पाला पड़ गया? No, you said nah, mass of whole universe is conserved. You prove it. You prove it right here, man. Otherwise, withdraw your words. Mass of whole universe is conserved. Prove it. When did you measure the mass of whole universe? Nobody measured the mass of whole universe. It is a common belief. We just believe that, yes, every evidence that we have seen so far supports our belief. So we say our belief must be correct only. Otherwise, if our belief was not correct, then we must have observed something violating our belief. But so far, in the world of scientific discoveries, we observed everything following our belief that mass is conserved, energy is conserved. That becomes our axiom. Similarly, my dear friends, there are 3 axioms of probability. Before we can answer all those questions, before we can know that what is the chance of an event occurring, what is the chance of occurrence of event, my dear friends, I propose 3 axioms of probability. Axiom number 1 is that any event in the world can never ever have negative value of probability. Any event in the world can never ever have negative value of the probability. Worst case, it will not happen, then there are 0 chances. Can you have minus 10% chances of an event happening? Huh? The tube light in this studio room will get damaged. What is the probability? Maybe 10%. Worst case or best case, it will not get damaged today. Then 0. If something is not happening, then there are 0 chances of happening. What are the chances that an earthquake will hit some part of the world today? Worst case, actually best case, earthquake will not hit any part of the world today. There will be no earthquake, then there are 0 chances of earthquake. You can never have negative chances. So even though it is an axiom, but it makes sense. It is an axiom, we cannot prove it, frankly speaking. We can only give an argument in favor of it. There is no mathematical proof. An event will never have negative value of probability. And then we have axiom number 2. Axiom number 2 is that probability of whole sample space is always 100%. Now, what is the proof of this axiom? If you're asking for proof of an axiom, then your expectation is wrong. An axiom cannot be proved. An axiom is nothing more than a belief. An axiom is nothing more than a belief. An axiom can never be proved. You cannot prove an axiom, no. Second axiom of probability is that probability of sample space is 1 because something will happen. So if random experiment is performed, something happening is 100% possible. There are 100% chances that something will happen. If you roll a die, 1 or 2 or 3 or 4 or 5 or 6, something will happen. So probability of sample space occurring, any part of sample space occurring is 100%. So probability of sample space is always going to be 100%. While these two axioms are still easy to digest, third axiom is a little inconvenient to digest, that if there are two mutually exclusive events, if there are 2 or 3 or 4 or 5 or 6 mutually exclusive events defined on the sample space, then the probability of their union will be, the probability of their union will be simply the probability of simply the sum of their individual probabilities. Can we prove this? Again, a wrong expectation. Axioms cannot be proved. Axioms cannot be proved. Okay, but I can give a little justification to you. I can give a little justification to you that union is like union is like realizing an event or an event occurring by the occurrence of either A happening or by the occurrence of B happening. Union is like that if A happens, then also you are okay. If B happens, then also you are okay. Then, my dear friends, I noticed that the chance of occurrence of this union of A and B, chance of occurrence of union of A and B is what? Union of A and B is water coming out of the tap. Water coming out of the tap. It can be satisfied even if the supply line A is closed. Supply line A is closed, but supply line B is open. So the chance of occurrence of water coming out in case there is no chance of water coming out from this supply line, even then you have the chances of water coming out is still equal to the chances of water coming from supply line B. Supply line B. And if supply line B was choked, if supply line B was choked and supply line A was having 50% chances of water coming out, you notice then also water finally coming out will have 50% chances even if other line is choked. Even if the second supply line is having a closed connection. So second supply line has been choked even then. First supply line is having 50% chances, so water coming out here will also have 50% chances. We notice that union can be satisfied either by satisfying A or by satisfying B. So the chances of water coming out will be 20% if only B works. And chances of water coming out will be 50% if only A works. In case both work, then you obviously have more chances. You obviously have more chances of water coming out. So my dear friends, this is the justification of this imaginary setup is justification of third axiom. But as I said, axioms are not to be proved. Axioms are not to be justified. Axioms are to be taken as it is. That if some people, if some scientists have proposed them, I'm going to accept them. Probability of any event is never going to become negative, number one. Probability of whole sample space will be one, number two. And probability of number of mutually exclusive events, union of mutually exclusive events, is always going to be equal to the sum of probability of individual events. Mutually exclusive events, I'm using a word here, mutually exclusive events. So let me tell you what is the meaning of that mutually exclusive events. First of all, I'm going to write A, B, C, etc., are A, B, C, etc., are mutually exclusive, events, etc., are mutually exclusive events. Now, what is mutually exclusive events? If A happens, then B doesn't happen. And if B happens, then A doesn't happen. In very simple word, they don't have any common. They don't have any common thing. So A intersection B will become an empty set. If A and B are mutually exclusive events, then A intersection B will become an empty set. They both can never happen simultaneously. Then we call them mutually exclusive events. Axiom number one, as I said, there is no definition of probability. The definition that have been taught to you, that probability is favorable elements upon total elements, is actually a scam. This is a scam. There is no such definition of probability, at least not a fundamental one. This is a very limited. This is the definition of probability in very limited cases. We will see those limited cases. As of now, I say it again, there is no definition of probability. There is no rule, no equation, nothing we know of probability except these three axioms. Axiom number one, that no event can ever happen negative probability. At least in worst case, event will not happen. So zero chances are there. Sample space, whole sample space has a probability of 1 because something will happen in the sample space. The whole sample space means you are covering every possibility. So something will happen in the whole sample space. Third axiom, if A and B are mutually exclusive events, then the probability of A union B will be the sum of probability of A and probability of B. My dear friends, ध्यान से समझियो, बहुत ध्यान से समझियो. We are going to build every other thing on the basis of these three axioms. Make a note of these three axioms in your mind and also in your notebook. Make a note of these three axioms in your mind and also in your notebook. ध्यान से समझियो. So let us rewrite them for just one more time. Probability of any event will always be non-negative. It can be zero. I mean, worst case, you'll have zero chance of something taking place. Probability of sample space, whole sample space is 100%, and probability of A union B, if A and B are mutually exclusive events, then probability of A union B will be equal to probability of A plus probability of B. Probability of A plus probability of B. Okay. This is how we have defined three axioms. Now, let's try solving a problem. Finally, one problem. First problem. Suppose the probability of raining today is 30% probable. Now, who told this? And how we obtained this 0.3, that's still a mystery. That's still a mystery, but let's say somehow we know this value. And suppose probability of having an storm today is 0.14. And suppose they can't happen simultaneously. Suppose it is known that they can't occur together. In real practical life, we know that there can be rain occurring with a storm, but let's say, to keep it very simple in the beginning, let's say that they can't occur together. Then what is the probability of a bad weather today? What is the probability of a bad weather today? You can solve this very easily. How you can solve this? Probability of a bad weather means either rain happens or a storm happens. I told you repeatedly that union represents R. And since they can't occur simultaneously, they become mutually exclusive events. They become mutually exclusive events. They become mutually exclusive events. So it's from the third axiom, it's going to be equal to probability of raining today plus probability of storm. Bad weather means if raining is happening, then also bad weather. If a storm is happening, then also bad weather. So either raining is happening or a storm is happening. Either raining is happening or a storm is happening. From third axiom, that probability is going to be 0.44. So I understand this axiom that no event can ever have negative value of probability, because it's obvious that worst case an event will have 0 chances of occurrence. I understand this also, that since sample space means what? Sample space means every single possibility. So I understand this also. That sample space means every single possibility. Then if sample space means every single possibility, then there are 100% chances that something will happen in the sample space. I don't understand this third one, sir. That's the problem. This is an axiom. An axiom is something that you have to accept. I gave you one logic of that water coming out of a tap. I gave you one logic of that water coming out of the tap. And also another logic is, if you have studied OR gate in basic electronics. You have studied OR gate in basic electronics? What is OR gate? OR gate is that if this is 1 and this is 0, then also you get 1. Or if this is 0 and this is 1, then also you get 1 here. That means OR gate gives you an output, even if one of them is giving you an input. So union is satisfied or by OR logic. That if rain happens, then also union is satisfied. Storm happens, then also union is satisfied. Union gets satisfied by the OR gate logic. Logic gate you have studied now, electronics and communication, basic electronics subject in the first semester of engineering. That is the logic behind third axiom. And you can solve these kind of very easy problems where probability of A is given and B is given and C is given, and all of them are mutually exclusive. Then you simply solve by adding. That's it. Now I take you to one real practical scenario, and that real practical scenario, the type 1 probability, the type 1 probability scenario. Before we go ahead, let me write 3 axioms for one last time. What are the 3 axioms? Axiom number 1, that an event can never have negative probability. Axiom number 2, that sample space probability will be sample space probability. Axiom number 3 is that axiom number 3 is that probability of A union B, if A and B are mutually exclusive, then probability of A union B will be equal to probability of A plus probability of B. Probability of A plus probability of B. How these 3 axioms came? Again, a wrong question. Axioms are not to be proved. Axioms are not to be proved. Axioms are to be believed. That this is an axiom, just like I believe that God is there. Similarly, I believe that these things are true. So far in the world, nobody has been able to prove them wrong. So yes, if something nobody can prove wrong, then it becomes a universal truth. I take you to the first scenario of calculating probabilities. And first scenario of calculating probabilities is dhyan se samajhiyo, because now we are entering into something seriously interesting. The first scenario of calculating probabilities, just to tell you that in the very first subtopic of topic number, this is the third topic we are doing, and the third topic we are doing is probability itself. And then, my dear friends, we started with 3 axioms of probability. One last time I'm telling, axiom means what? Axiom means what? Axiom means a common belief that just like mass of the universe is conserved, now we go to the first scenario of calculating probabilities. And the first scenario of calculating probabilities is finite sample spaces. Finite sample spaces. Finite sample spaces with equally likely events or equally likely outcomes. Finite sample spaces with equally likely outcomes. Finite sample spaces with equally likely outcomes means what? Means that if you consider rolling a die as a random experiment, rolling a die as a random experiment. It has sample space that is finite. Only 6 countable elements are present. Moreover, they all have equal probability. That means they all have equal chances of turning. They all have equal chances of turning. Okay, so this is an example of a finite sample space. 1, 2, 3, 4, 5, 6 possibilities are there, finite, not infinite possible outcomes, but you have finite possible outcomes, finite sample space, and there are equally likely outcomes. And there are equally likely outcomes. So 1 and 2 and 3 and 4 and 5 and 6 all have equal chances if the die has been manufactured properly. If a coin is tossed, if you are tossing a coin, if you are tossing a coin, my dear friends, sample space will be either a head or a tail. It is a finite sample space, and both are equally likely, head and tail. If the coin is manufactured in a proper way, in a correct way, both are equally likely. Then you can think of a random experiment drawing a card from the pack of 52 cards. Drawing a card from the pack of 52 cards, it has 52 possible elements, but still its sample space is finite. Its sample space is finite because you can get the ace of spade, you can get the king of spade, you can get the queen of spade, you can get the jack of spade, you can get the 10 of spade, you can get up to 2 of spade. Then you can get ace of club, king of club, queen of club, jack of club, you can get 10 of club, you can finally get 2 of club. Then you can get, so rolling a die is an example of finite sample space with equally likely outcomes. Similarly, my dear friends, tossing a coin is again an example of finite sample space with equally likely outcomes. Each outcome is having equal chances. Then we call it equally likely outcome. If you are drawing a card from the pack of 52 cards, you might get ace of diamond and king of diamond and queen of diamond and jack of diamond and jack of diamond and 10 of diamond and finally 10 of diamond and finally 2 of diamond. Similarly, there is one more color remaining, no? So spade you have listed, club you have listed, diamond you have listed, and heart is remaining. So you might get ace of heart, you might get king of heart, you might get queen of heart, you might get jack of heart, you might get 10 and maybe up to 2 of the heart. So what is the sample space? Sample space is having 52 possible elements, and each element of the sample space is having barabar chances. Each element of the sample space is having exactly the same chance. Each element has same chance. We call it equally likely outcome. These are the examples of finite sample spaces with equally likely outcomes. We are going to, on such finite sample spaces, we are going to start with a question that what will be the probability of each outcome? What will be the probability of each outcome? If each outcome is equally likely, let's assume something for it. If each outcome is equally likely, let's say probability of each outcome is small p. Writing let here is a very important thing. So this we are assuming that let small p is representing the probability of what? Probability of each individual outcome. Let's say small p is representing probability of each individual outcome. Small p. Now we go with the axiom number 2. Now we go with the axiom number 2. Axiom number 2 says that sample space, the probability of sample space, whole sample space is 1. But whole sample space is simply the union of element 1 and element 2 and element 3. Whole sample space is simply the union of element 1, element 2, element 3, element 4, element 5, and then finally element number capital N. Where capital N, how much is the value of capital N in case of dice? Tell me.
6, sir.
6, sir.
6. And how much is the value of capital N in third example?
52, sir.
52, sir.
52. 1, 2, 3, 4, 5. 1, 2, 3, 4, and then 9. So 9 plus 4, 13. 1, 2, 3, 4, and then 9. 9 plus 4, 13. 1, 2, 3, 4, and then 9. 9 plus 4, 13. 1, 2, 3, 4, and then 9. 9 plus 4, 13. So 13, 13, 13, 13 becomes 52. Capital N value is 52 in the example of cards, and capital N value is 6 in the example of dice. I assume that let probability of each outcome is small p, and that's what is our target. This is our target. We start with axiom number 2. Axiom number 2 says probability of whole sample space is 1. That whole sample space is simply the union of element 1, element 2, element 3, element 4, element 5, element 6. Element 1, element 2, element 3, element 4, element 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Whole sample space is simply union of each element or each possible outcomes. Now I use ध्यान से समझियो. Now I use axiom number 3. Now I use axiom number 3, and axiom number 3 says that if one event is mutually exclusive to the second, and then they are mutually exclusive to the third, fourth, fifth, and nth, then probability of their unions will be what? Probability of their unions will be P of E1 plus P of E1 plus P of E2 plus P of E3 plus P of En plus P of En is equal to 1. But since each element is equally likely, this is also small p, and this is also a 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 small p. I get a small p n number of times, capital N number of times. So n multiplied by p becomes the left hand side, and I get the small p value. And I get the small p value equal to 1 upon n. I get the small p value 1 upon n. Now let an event A be defined as let an event A be defined as now let an event A be defined as the event containing 4 elements. Now let An event A is defined on the sample space that's containing a small n number of elements. That's containing, I'm defining an event on the sample space A that contains a small n number of equally likely outcomes. A small n number of equally likely outcomes. I'm defining an event on the same sample space that contains a small n number of equally likely outcomes. Small n number of equally likely outcomes. ध्यान से समझियो, बहुत 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 ध्यान से समझियो. So small n number of outcomes, my dear friends, then that event A can be written as union of ith element and jth element and kth element and so on and so forth. Again from third axiom, I can write probability of EI and EJ and EK, the union of probability of EI, EJ, EK as the sum of probability of EI and probability of EJ and probability of EJ and probability of EK and probability of EN, like that, like that, like that, like that, like that, like that. How many such elements have been included? Small n number of such elements. So I'm going to get how many times this small p coming here? Small p coming here, how many times? Small n number of times. The small p is coming here, small n number of times. And if you're adding small p, small n number of times, what exactly are you going to get? बहुत ध्यान से समझिए.
Sir, once explain equal. What is mean
I'll
by
explain whole thing again. Don't worry. So let an event A is satisfied by satisfying a small n number of elements. I'm just defining an event A that is satisfied by satisfying a small n number of elements, a small n number of outcomes. Then it can be written as the union of those small n number of outcomes. Then it can be written as union of those small n number of outcomes. Now union from axiom number 3 is equal to probability of each possible outcome, all those small n number of outcomes, small n number of outcomes. You keep adding small n number of outcomes, but each outcome is having a probability of 1 upon n. Each outcome is having a probability of 1 upon n. Each outcome is having a probability of 1 upon n. And this you are doing n number of times. Now you tell me what exactly are you getting? Now you tell me what exactly are you getting? Hello, people.
one, sir?
If no, if you keep adding 1 upon n, 1 upon n, 1 upon n, 1 upon capital N, 1 upon capital N, 1 upon capital N, small
by
n
n,
number
sir.
of times,
Small n by capital N.
small n by capital N. What was capital N? Capital N was the number of all possible outcomes in the sample space. And what is small n? Small n, the number of outcomes in which you are, the number of outcomes in which you are interested. Small n is the number of outcomes, that part of the sample space in which we are interested, that part of the sample space that favors me. And therefore, my dear friends, in numerator, you keep that part of sample space which favors me, and in denominator, you keep number of total possible outcomes. people usually present this formula as some definition of probability. This formula is actually obtained for finite sample spaces with equally likely outcomes only. And notice that I obtained this formula with the same axioms that I defined in the very beginning. I said that the whole probability is all about whole probability. Everything that you are ever going to study about probability is all about these three axioms. That's it. These three axioms are everything, actually. These three axioms are everything. And we obtained this so-called favorable outcomes upon total outcomes formula by using our three axioms. But I know that probability initially is a little puzzled topic. Probability initially is a little struggling topic. We struggle a lot to digest probability initially. But once you start understanding it, then you are going to enjoy it like anything. So I do this whole thing once again. I do this whole thing once again for you. So for you, I'm going to do this whole thing just once again, very quickly. So make sure that you remain very attentive. बहुत ध्यान से समझियो. Let us erase the whole thing in one stroke. And erase this thing also in one stroke. This thing again. So be very attentive, people. We will do this entire story just once again, very quickly. That today we started understanding what is probability. Probability is chance of occurring of something. And what is the chance that it will rain today? Probability means chance of occurrence of something. What is the chance that a thief will be caught today? What is the chance that an LED bulb will go out of service today? What is the chance that you'll get a call right now? What is the chance that a particular batsman will score a 50 today? What is the chance that there will be some earthquake today in some part of the world? What is the chance that it will storm today? What is the chance that a screw will be defective? What is the chance that a bearing will have 20 million revolutions of life? What is the chance that the shaft that you supplied to a manufacturer will be rejected? What is the chance that humidity in the air today will be more than 70%? What is the chance? Chance. You are surrounded by chance. So you want to know what is the chance of occurrence of something? What is the chance of occurrence of something? Now that chance of occurrence of something, it has been given a technical name, probability. First of all, they gave it a technical name to scare you, probability. Now, how do we calculate that probability? How do we know that what is the chance of occurrence of something? Chance of occurrence of something, we are going to understand. But before we understand that, we said that there are three fundamental laws of probability and they can't be proved. Three fundamental laws of probability and they can't be proved. Guys, I assure you that there are people who can solve problems based on probability. but there are very few people who actually understand probability. Just remembering the methods to solve and mugging up the algorithm, that is one thing. But actually commanding this topic is a rare thing. If there are 100 maths teachers, I can claim this, that 70% teachers can solve problems. They can solve problems, not a problem. That's not a challenge. They can solve problem because they have understood the algorithms. They have understood, Acha, this type of problem, I will do this. This type of problem, I will do this. But only 20% of the teachers themselves would actually understand probability. I'm damn serious here. Three axioms of probability. Three axioms of probability are nothing but a belief. Can we prove them? No. Can we disprove them? No again. They cannot be proved. They cannot be disproved. Something cannot be disproved. It becomes a law. First axiom is that an event will always have zero. An event will always have zero or positive chances of occurrence. And an event in worst case will have no chance of occurrence. Then we say zero. Second axiom is that the probability of whole sample space is going to be 1. Why probability of whole sample space is going to be? Why probability of whole sample space is going to be 1? Probability of whole sample space is going to be 1 because, my dear friends, so some preparing live stream is coming here and I don't know how to remove it. Even though live stream is very smoothly running on YouTube. So third axiom is what? Third axiom is, chalo, I'll have to take it to here. Third axiom is what? Third axiom is that probability of A union B will be equal to probability of A plus probability of B if A and B are mutually exclusive. If A and B are mutually exclusive events. So what are mutually exclusive events? Mutually exclusive events are never going to happen simultaneously. They cannot co-occur. They cannot simultaneously occur. Mutually exclusive events can never occur simultaneously. Okay? This is the third axiom. As I said repeatedly, that only third axiom is a little challenging to understand. That why union is equal to PA plus PB. As I said, don't apply much brain on axioms. Let's move on to the next thing. And the next thing is, now we can do the analysis of one possible scenario of probability. And one possible scenario of probability is finite sample spaces, finite sample space with equally likely outcomes. What is this equally likely outcome? What exactly is this equally likely outcome? Equally likely outcome means that each outcome is having barabar chances. Each outcome is having same chance. For example, these are the examples of finite sample spaces. You have 1, 2, 3, 4, 5, 6 finite. You have 1, 2 finite. 1, 2, 3, 4 plus 9, 13. 1, 2, 3, 4 plus 9, 13. 1, 2, 3, 4 plus 9, 13 again. 1, 2, 3, 4 plus 9, 13 again. So you have 52. You have 52 total elements. Finite sample space with equally likely outcomes. Finite sample space with equally likely outcomes. These are the examples of finite sample spaces with equally likely outcomes. Now, equally likely means same chance, same chance, same chance, same chance, same chance, same chance. Each element has same chance. We start with the axiom number 2. Axiom number 2 is what? Axiom number 2 is probability of whole sample space is 1. But whole sample space is nothing but union of element 1, element 2, element 3, and then union of element number capital N. What is capital N? Capital N is all elements in the sample space is equal to 1. Now I use axiom number 3. How can I use axiom number 3? Because if 2 happens, then 3 will not happen. If 3 happens, then 5 will not happen. If 5 happens, then 6 will not happen. If 6 happens, then 1 will not happen. If 1 happens, then 4 will not happen. So all become mutually exclusive. All of the elements become mutually exclusive. If all of the elements become mutually exclusive, then even union E2, union E3, union E4, even union E2, union E3, union E4, the third axiom says their probability will be the sum of their individual probability. Their probability will be the sum of their individual probability, but all of them are equally likely. 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 You are essentially adding small p, small p, small p, small p. How many times? You are adding small p, small p, small p, small p, n capital N number of times. Small p, small p, small p, small p, capital N number of times. So you get small p is equal to 1 upon capital N. This is the probability of each outcome. This is the probability of each outcome. Now suppose an event A contains small n outcomes. For example, getting an even number when you are rolling a die, getting an odd number, you are rolling a die, getting a red color card when you draw a card, getting a jack or a 10, getting a jack or a 10 of club or diamond. Just like I have said it, if you define that kind of event. So let's define an event that contains a small n number of outcomes. Then how that event A is satisfied? That event A is satisfied by satisfying ith element union jth element union ऐसे करके how many of them? How many of them? Small n number of them. Small n number of them. So an event is nothing but a union of some elements that we are interested in. We are interested in only jack of club, 10 of club, jack of diamonds, and 10 of diamonds. We are interested in only jack of club, diamonds, jack of diamonds, 10 of club, and 10 of diamonds. ध्यान से समझियो, बहुत ध्यान से समझियो, because all this is going to become very interesting now. Now we are going to apply for one last time axiom number 3. Now we are going to apply axiom number 3. Axiom number 3 says that probability of A union B union C will be simply equal to probability of first event plus probability of second event plus probability of third event plus probability of third event plus probability of small nth event. My dear friends, but this is also 1 upon capital N, and this is also 1 upon capital N, and this is also 1 upon capital N. So you are adding 1 upon capital N how many times? Tell me. You're adding 1 upon capital N how many times?
Small n times.
A small n number of times. There people said that probability of an event is the number of elements favorable to that event upon total number of elements. There people said that probability of an event is the ratio of the favorable elements and total elements. Is that universal definition of probability? No. So people present this usually as a definition of probability. That's wrong, because this is only valid for finite sample spaces with equally likely outcomes. This particular thing is valid only for finite countable sample spaces with equally likely outcomes. Let's solve some problems based on this. Let's solve some problems. Let's solve. Let's solve some problems based on this.
Sir, here
Mhm.
P is not defined. Like P be the probability of each individual.
A is not.
P is the probability of each individual outcome. It is not defined here. I just want to remind.
I'm not able to understand. Say it loud.
Here, P is the probability of each individual outcome.
Each
Earlier
individual outcome, yes.
earlier you defined and here you not defined. Just I want to mention that. So
Okay. Actually, space was limited, so I thought I'm not going to write that.
okay.
It was a recap, anyways, so that is understood. It was just a recap. Okay. So wherever you have a finite sample space, a single finite sample space with equally likely outcomes, you can apply this. For example, suppose I say that what is the probability of getting an even number when you roll a die? Now, this is such an easy thing. Total sample space is 1, 2, 3, 4, 5, 6, and your event contains only 2, 4, 6. So probability of your event is going to become small n upon capital N. Small n is 3, capital N is 6. That becomes 1 upon 2. Other way to do this, this is one way to do this. Other way to do this is satisfied either by getting 2, is satisfied either by getting 2 or by getting 4 or by getting 6. Now use axiom number. Which axiom? You tell me. After this, which axiom do we use? Axiom number
Axiom
1 or
3. Axiom 3.
3? Axiom number 3. So probability of 2 and probability of 4 and probability of 6. So probability of 2 is also 1 upon 6, and this is also 1 upon 6, and this is also 1 upon 6. That becomes 3 upon 6, that is 1 upon 2. So you get exactly the same result following either the axiom or that favorable upon total thing. Okay. Now let us solve one more problem. Let's say two coins are tossed. What is the probability of getting at least what is the probability of getting at least one head? Once again, sample space is H and T, and then T and H, and H and H, and T and T. What is the event you want? Event you want at least one head, at least one head, at least one head. So naturally, at least one head, at least one head, at least one head. So how many outcomes favor you? 3. How many total outcomes are there? 4. Probability of getting at least one head becomes 0.75. Probability of getting at least one head becomes 0.75. As simple as that. These are some simplest questions of probability. We are actually going to enter into much more interesting problems. And today itself, we will enter into those interesting problems. Let's solve the next one. We have started with very basic and simple problems, but don't worry. Gradually, we are going to solve problems that you must otherwise have struggled. Okay, so here we go with the fourth problem. Let's say 2 dice are rolled. Two dice are rolled. What is the probability of getting sum of both outcomes as a perfect square? Getting sum of both the outcomes as perfect square. Again, that's an easy one. By the way, if two dice are tossed, if two dice are rolled, then there are number of possibilities. First possibility is that you might get 1 and 1, so sum becomes 2 minimum, or you might get 6 and 6, so maximum sum becomes 36. Maximum sum becomes 36. But on first one you get 1 and second one you get 2, or on first one you get 2 and second one you get 1. On first one you get 2 and second one you get 1. So sum becomes 3 in 2 possible ways. Similarly, on first one you
Sir,
get
last one 6 and 6 12 now, sir. Sum.
I'm so sorry. In my mind I was having product. So sum becomes 12. And then 5 and 6 and 6 and 5. These 2 ways there exist to get the sum 11. And then on the first one you are going to get 1, and second one you are going to get 3. On first one you get 2, and second one you get 2. On first one you get 3, and second one you get 1. And that gives you 3 ways in which sum can be 4. And then, my dear friends, we are going to get on first one we are going to get 4, and second one we are going to get 6. On first one you are going to get 5, and second one again 5. On first one you get 6, and second one again you get 4. However, it is going to become unmanageable most of the times, but I want to cover this problem even now as a finite sample space. It's actually a compound sample space because two dice are rolled, but later on we will realize that we can solve such problems only by converting them into finite sample spaces. Just like previous problem, two dice are rolled, two coins are tossed. So there are three ways in which the sum can become 10. There are three ways in which the sum can become 10. Now let me just shift this part so that we have 5, 6, 7, 8, 9. Yes. Shift this little bit more. Now there are on the first one you are going to get on the first one 4,6. Ticket. On the first one you get 1, second one you get 4, or on the first one you get 2, second one you get 3. On the first one you get 3, second one you get second die you get 2, and on the first one you get 4 and second one you get 1. So this way there are 4 tariqas existing to get the sum as 5. Similarly, my dear friends, we are going to get sum becoming 9 in either 4,5 or 3,6 or 6,3 or 5 on first die and 4 on the second die. So sum can become 9. And then we are going to get 3 more possibilities. One is 6, another is 7, and yet another is 8. 6 is having 1 and 5, and then 2 and 4, and then 4 and 4, 3 and 3. I'm sorry. 6 is having 3 and 3, also one possibility, and 4 and 2, also one possibility, and finally 5 and 1, another possibility. 8 is having 2, 6 as one possibility, 3, 5 as another possibility, 4, 4 as yet another possibility, 5, 3 is yet another possibility, and 6, 2 is yet another possibility. And then we are going to have 7. 7 is having 1, 6 as one possibility, 2, 5 as yet another possibility, 3, 4 is yet another possibility, 4, 3 is yet another possibility, and 5, 2 is yet another possibility, and 6, 1 is yet another possibility. Wow, this is such a beautiful pyramid, no? This is such a beautiful pattern we obtained here.
Nominal distribution.
Normal distribution. We will see. Even entropy principle is connected to probability. And there is a lot of beauty that we are going to unfold as we proceed further and further and further and further and further. But as of now, you don't have any choice but to wait. A lot of patience you will have to show in initial 4 or 5 classes. And then you are going to enter into a world of beautiful, beautiful, beautiful dimensions and beautiful landscapes of probability. My dear friends, as of now, we can see that there is one way to obtain either the sum 1 or 12. There are 2 ways to obtain either the sum 3 and 11. There are 3 ways to obtain either the sum is 4 or the sum is 10. There are 4 ways to obtain either the sum 5 or 9. There are 5 ways in which the sum can be 6 and 8. And there are 6 ways in which the sum can be 7. I want the sum to be a perfect square, and I'm just going to count the total number of outcomes. Total number of outcomes are 3 plus 2 plus 1, 5, and 3 plus 2 plus 1, 5, 5, 5, 10. And then 4 and 4 becomes 18, and then 5 and 5 becomes 28. Final 6. Now 34 only. 3, 3, 6, 3, 3, 6. 6 plus 6, 12. 12 plus 4, 16 plus 4, 20, 25, 30, 36. So there are 36 total outcomes available, out of which there are total, how many outcomes available? There are total 36 outcomes available. And how many are favorable to us? How many are favorable to us? Is it a problem of finite sample space? Will depend upon your perspective. It is a single finite sample space. If you list all possible outcomes, if you list all possible outcomes like this, then it becomes a problem of single finite sample space with each pair equally likely, 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 equally likely. Each pair is having same chances of becoming reality. So how many of them are favorable to you? Perfect square means the sum becomes 4, or the perfect square means the sum becomes 9. So how many ways sum becomes 4? How many ways sum
7
becomes
ways.
4? Sum becomes 4 in 3 possible ways. And how many ways the sum can become equal to 9? The sum can become equal to 9 in 4 possible ways. My dear friends, total number of favorable possible ways in which the sum can be perfect square is 7. So probability of A is going to be what? Probability of A is going to be 7 upon 36. Probability of A is going to be 7 upon 36. Can you calculate probability of product being perfect square? If 2 dice are rolled, can you calculate the probability of product of outcomes becoming a perfect square? Now, product becoming a perfect square. Let's see. 2 dice are rolled. Total number of outcomes 36. How many are favorable to you? How many are favorable to us? Look, the product of 1 and 1 is also a perfect square. The product of 2 and 2 is also a perfect square. The product of 3 and 3 is also a perfect square. The product of 4 and 4 is also a perfect square. The product of 5 and 5 is also a perfect square. The product of 6 and 6 is also a perfect square. The product of 6 and 6 is also a perfect square. No, one more possibility. Product of 1 and 4 is also a perfect square. And one more possibility. Product of 4 and 1 is also a perfect square. So there are 1, 1, 2, 2, 3, 3, 4, 3, 4, 4, 5, 5. They are favorable to you. And then there is also I should better reduce the size of this one. So how many are favorable to you if you want the sum to be perfect square? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Any other perfect square we are getting? 4 4s are 16. Actually, 1 is a perfect square, 4 is a perfect square, 9 is a perfect square that can be a product of only 3 and 3. 16 is the next perfect square. It can be a product of 4 and 4 only. Yes. 25 is a perfect square. We are good. So 6 plus 2, 8 favorable ways are there. We get the probability as 8 upon 36. 8 upon 36 becomes 2 upon 8, 4, 2 8 and 4 9, 36. So 2 upon 9.
2 by 9, sir.
2 by 9, yes. 2 by 9. So these are the examples of some becoming, finite sample spaces. Actually, this is treating this as a single finite sample space is again a subjective matter. If you can count all possible outcomes, then it always becomes a single finite sample space. But rolling 2 dice or tossing 2 coins or rolling 3 dice, 4 dice, or tossing 5 coins is actually not a single finite sample space. It's called compound sample space. And we will deal with it later. As of now, we are able to list, in case of 2 dice are rolled, we are able to list all 36 outcomes in a matter of 1 or 2 minutes. So we converted this problem into a single finite sample space. We converted this problem into a single finite sample space. Dhyan se samajhiyo as I take you to the next problem.
Sir,
Huh?
here how we can say that equally likely outcomes, sir?
Because each pair is having, what is the argument that you are going to give that 6 comma 1 is having more chances than 6 comma 5, or 2 comma 3 is having more chances than 6 comma 4, or 1 comma 2 is having more chances than 3 comma 4. Because each dice is having equally likely outcomes, 6 outcomes. So 6 into 6, all 36 outcomes will be equally likely even if you roll 2 dice. If you roll 1 dice and let's say 6 comes, then other dice gets affected. That, oh, first dice returned 6. Ab to main bhi 6 aunga. Now I will also turn 6. Does that happen? Then one dice looks at another dice and asks, which number? Today 5, huh? Okay, I will also be 5. So there is no way that they can affect each other. And therefore, all 36 possibilities are having same chances. There are 36 possibilities here, and all these 36 possibilities are having equal chances. Every possibility has exactly the same chance. And why won't it have the same chance? Do you have any argument against it? No.
No, sir.
Huh. So guys, we are going to move to the next kind of problem. We are done with three axioms of probability, and then we are done with finite sample space with equally likely outcomes. Now I take you to the next one. And the next one is addition law of probability. What is addition law of probability? Addition law of probability is very simple. A union B is written as n of event A plus number of elements in event B minus number of elements in A intersection B. If I divide by capital N, 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 can you please tell me what is this representing and what is this representing and what is this representing and what is this representing? And guys, mind it that I have in your initial journey, I told to you number of times this set theory is going to become a very crucial thing for your future problems. So what is this representing? This small n upon capital N, small n upon capital N, small n upon capital N, small n upon capital N. Three axioms of probability. Axiom number one, no event can ever have negative value of probability. Second axiom, whole sample space will have 100% chances of occurring. And third axiom that if A and B are mutually exclusive, if A and B are mutually exclusive, then my dear friends, it will be its union, probability of its union will be probability of A plus probability of B, probability of A plus probability of B. Then we dealt with finite sample spaces with equally likely outcomes, and there the probability of any event will be equal to small n upon capital N. Small n are the favorable number of outcomes and capital N is the total number of outcomes. Now you tell me, I'm presenting addition law of probability. Addition law of probability is NA plus NB minus. This is something I proved not once but twice in previous class. Previous class, I derived this. And if you want, we can do it for your satisfaction. We can do it just once more. That A union B is what? A union B is the sum of A minus B. A union B is the sum of A minus B and B itself. But what is A minus B? A minus B is A minus A intersection B. Yesterday I told you now that there is mathematical proof also possible. Look, this is the mathematical proof of, what do you call this principle? What is the name of this principle
Mutually
that
Inclusive
no,
exclusive.
what is the name of this principle?
inclusive exclusive principle.
Inclusion exclusion principle. So now I divide by capital N, divide by capital N, divide by capital N. You tell me now, what is this term representing? This term is representing probability of A union B. And what is this term representing? This term is representing probability of A. And what is this term representing? This term is representing probability of B. And what is this term representing? This term is representing probability of A intersection B. This term is representing probability of A intersection B. My dear friends, this final law that you see in front of your eyes is known by the name addition law of probability. This final law that's there in front of your eyes is known as addition law of probability. ये final नियम जो आपके सामने है इसे कहते हैं addition law of probability, and this is one beautiful law. How many problems we solved so far?
4, sir.
5, sir.
5. Here is the sixth one. Probability that it will rain today is 0.3, and probability that it will storm today is 0.14, and probability that it will rain with storm, probability that it will rain with storm is only 5%. Find out the probability of bad weather. Find out the probability of bad weather. You remember we solved this problem today, but at that time I said they cannot happen together. At that time I said they cannot happen together. At that time I said that they can not happen together. Now I'm saying that they can happen together. So if they can happen together, how do we solve the probability of a bad weather? Probability of bad weather means rain happens or storm happens. Rain happens, then also there is a bad weather, or storm is coming, then also there is a bad weather, or storm is coming, then also there is a bad weather. Okay, rain or storm, both ways you have a bad weather. So R means what? I told you repeatedly that R means union. Union is something that gets satisfied by either rain or storm or both. Bad weather means either barish is happening or tufan is coming, or both barish and tufan are coming. Either rain is happening or storm is happening, or both rain and storm are happening. My dear friends, we can write this. Probability of raining plus probability of storming plus minus probability of raining as well as storming. Probability of raining as well as storming. So probability of raining is 0.3, probability of storming is 0.14, and probability of raining plus storming is 0.05. So I get, where is the calculator? I get 14 minus 5. So basically we get 39% probability of bad weather. Now this is a little surprising. 30% chances are there for rain and 14% chances are there for storming. So total is 44%, but the probability of bad weather is only 39%. Probability of bad weather is only 39%. What the hell is happening? There are 30% chances of raining and there are 14% chances of storming. So total is 44%. But when we calculate the probability of bad weather, we are getting less than 44. What the hell is happening here? What the holy hell is happening here? I will tell you. And this is when Venn diagram becomes a magical thing. This is when the Venn diagram becomes a magical thing. In the Venn diagram, always start with the center, okay? Always start with the center, always start with the center, always start with the center. Now, in the 30% of rain, remaining space will represent only 25%. And in the 14% of storming, remaining space will represent only 9%. If common space is representing 5% already, if common space is representing 5% already, then in the remaining space of storming, we have only 9%. And in the remaining space of raining, we have only 25%. And now if you don't believe me, you define this part as event A and this part as event B and this part as event B and this part as event C, and all three are now mutually exclusive. So tell me, what will be the probability of a bad weather? Probability of bad weather is going to be equal to simply the probability of this white part plus probability of this green part plus probability of this yellow part. Add them together and you get 39%. Wow, 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 wow. Lovely. What a problem. Awesome. And it's a trapping problem. Many people will get trapped and they might answer 44 at least. They might answer 44, and some of the people might even answer 44 plus 5, that is 49%. 49% is not the answer. Answer is 39%. I wish we could solve more problems like these, but I'm so sorry, I have next session waiting for me. But we will solve just one more problem. We'll solve just one more problem, just one more problem, just one more problem. I'm going to just modify this problem only. We'll solve one more problem. Let's say we are interested in calculating the probability of no bad weather. Calculating the probability of no bad weather. What I want to calculate here? I want to calculate no bad weather. No bad weather means what? No bad weather. ध्यान से समझियो. And for a moment, let's say that I have not drawn this Venn diagram. So no bad weather probability will become equal to no bad weather probability means that you are going to have no rain. You are going to have no rain and also you are going to have no storm. No bad weather means no rain and no storm. No rain and no storm. Now, no rain and no storm means what? No rain and no storm means rain complements intersection storm complements. Rain complement, intersection, storm complement. I told you, if you have not attended previous 2 classes of probability, please go back and finish those 2 classes. Then only you will have the best taste of solving these problems. No rain and no storm. Now, my dear friends, we get no rain means everything other than rain. Rain complements. No storm means everything other than storm. Storm complements. And means what? And means intersection. Both happen simultaneously, co-occurrence of both the events. De Morgan's theorem says that R complement intersection S complement can be written as R union S complement. R union S complement. My dear friends, R union S complement can be written as 1 total 100%. Total sample space is always 100%. So if total sample space is always 100%, any event plus the complement of that event will become anything plus the complement of that thing will become 1. So complement can always be written as 1 minus that. So probability of complement of something can always be written as 1 minus probability of something. You remember you calculated this already in previous problem? You remember you
0.39, sir.
calculated
Yes, sir.
0.39 exactly. 0.39. So if you calculated this 0.39, you are going to get 0.61 as the final answer. But Venn diagram is the best way. In Venn diagram, do remember, always start at the center. Always start at the common area. At the time of drawing Venn diagram, always start at the common area, common area, common area, common area, common area. Then you would have got 39, remain from 100%, you subtract that 39, remaining thing, you get 61%. Thank you so very much, people. Thank you so very much, people.
Sir, tomorrow when our class will be started?
I will update on the group.
Okay, sir. Thank you.
Mm, mm.